Hi, everyone. Hello and welcome to the first Knauss Fellow Lunch and Learn. I am Jory Barley, a current Knauss Fellow with the NOAA Center for Satellite Applications and Research. The current Knauss Fellow cohort, as is true of every year, has done some wonderful things previous to this experience and are working in important and impactful positions in marine policy. We are very excited to share with you all that this group has accomplished and will accomplish throughout this year. It is my pleasure to introduce our first speaker, Caitlyn Czajkowski. She is a current Knauss Fellow from the Delaware Sea Grant and is placed in Senator Chris Coons' office. She is also pursuing her master's in natural resources at Delaware State University with a focus in aquaculture. With that, I will turn it over to you, Caitlyn.
Thank you, Jory. Let me just get my screen up. Okay. So thanks for tuning in, everybody. I'm going to be talking about my thesis research, which was novel approaches to combating Vibrio, sput, and oysters. So I'm going to start us off with just some general backgrounds about aquaculture, just to get everybody on the same page. So aquaculture is a rapidly growing industry in the United States. The graph on the right shows the increase in oyster sales since the late 90s. So you can see there's been pretty steady increase in the industry since then. Despite this growth, there are some hurdles the industry faces. One of them is a pathogenic bacteria called Vibrio, which I will go into more detail a little bit later. But it's thought that warming waters from climate change may be impacting the prevalence of Vibrio. And there are treatments to help remove Vibrio from oysters, but they're prohibitively expensive. Since oyster aquaculture involves growing oysters in coastal waters, that means they're directly exposed to the environment, and that makes them susceptible to pathogens and contaminants that are present in the environment. This can be enteric bacteria and viruses or Vibrio bacteria, along with other environmental hazards like heavy metals. The images below are just two examples of different types of oyster aquaculture. The image to the left is a floating bag system. The one on the right is a rack and bag system. So really method for oyster aquaculture depends heavily on where you're growing them. Enteric bacteria and viruses are bacteria that typically exist in digestive systems of humans and animals. Majority of them are harmless, but some are pathogenic. The most common you've probably heard of is fecal coliforms, which are usually used to test for fecal contamination and can be indicative of more dangerous pathogenic bacteria being present, like Salmonella, E. coli, or Enterococcus. Viruses can also be associated with contaminated waters. They're not as easy to remove from oysters, but for the most part, enteric bacteria can be reliably removed from oysters via a process called depuration, which I'll talk more about later. And that brings us to Vibrio, which is a little bit different than those bacteria. So Vibrio are naturally occurring bacteria. They're present in coastal and estuarine waters, especially in warmer climates. When it comes to disease in humans, we're primarily concerned with Vibrio vulnificus, which you'll see abbreviated VV, and Vibrio parahemolyticus, which you'll be associated with VP. Both species are present in estuarine waters. They're not associated with pollution or anything like that when it comes to fecal contamination. So when it comes to disease in humans, VV is typically associated with a more serious disease, but is a much rarer infection. VP is more common, but doesn't cause a severe disease. There are virulence genes or factors associated with VP. Those are the TDH or TRH genes. Typically, Vibrio is contracted via the consumption of raw oysters. That's why you may have heard people say, don't eat oysters in the summer. But there are other ways you can contract it, such as handling raw seafood or through environmental exposure from wounds. The range and seasonality of Vibrio is thought to be expanding. And you can see on this graph to the right, which is data obtained from the CDC's cholera and other Vibrio illness surveillance system, that there's been a steady trend of increasing infections since 1996. So how do we remove bacteria from oysters and make sure consumers are getting safe oysters? So one of the processes is called depuration. Depuration uses the natural filtering activities of oysters to help purge them of contaminants. In this process, oysters are held in clean seawater, which encourages their natural pumping activity, and over time, contaminants are expelled. It's effective at removing fecal bacteria. One of the benefits is that it doesn't kill oysters that are treated It keeps them fresh and alive, which also makes it attractive to consumers and farmers. On top of that, the equipment that you need to treat oysters with depuration is not very high tech or expensive. It's really just a tank with clean water flowing through. And despite the benefits of depuration as a post-harvest treatment, it's not consistently effective at removing Vibrio. It's thought this is potentially because Vibrio becomes attached to the gut of the oyster or is part of the natural gut flora. So if depuration doesn't work on Vibrio, what does? So there's other post-harvest processing, which I'll refer to it as PHP. So these processes are largely employed to help eliminate Vibrio, although they're effective against all bacteria. This is especially important in summer months in southern states where Vibrio prevalence can be fairly high. And there's 4 primary methods that I'm going to talk about and go over just very briefly: individual quick freezing, cool pasteurization, hydrostatic pressure, and irradiation. As I go through them, you'll see that while they are by and large effective, there are some issues associated with these treatments. The first, individual quick freezing. Oysters are shucked and frozen in this method. Generally, this method is in a different market. These oysters are not being served on like a fresh half shell market. They're being sent inland to areas that don't have as much access to fresh seafood. The next is cool pasteurization. So this is a thermal treatment using warm water that raises the internal temperature of oysters to kill pathogens. This does result in killing treated oysters. It has a minimum shell stock requirement, so you have to have a large throughput of oysters to keep it economically viable. You need specialized equipment. There's royalty and licensing fees to developers, so overall high initial capital needed to use this. Hydrostatic pressure is similar. This uses a high pressure to eliminate pathogens. Thought it could make shucking easier and faster. Again, kills treated oysters. There's some data lacking on just how effective it is against Vibrio, but is accepted generally to be effective against bacteria. It also requires specific machinery. You need additional skilled workforce to operate the equipment. So similarly, high initial capital. The final irradiation. In this process, oysters are treated with gamma radiation to kill pathogens. It's very effective at reducing all pathogen levels, including Vibrio. You can treat a very high volume of oysters quickly. Of course, kills the treated oyster. There can be a consumer bias just because of the relationship between irradiation and radiation. Generally, due to the very high cost of these facilities, they're accessed from via central processing facilities, and high initial capital needed, and you need a high traffic of product coming through these facilities to remain viable. A really important component of the oyster aquaculture industry is small independent growers and processing plants. So generally, it's just unfeasible for these small businesses to install and maintain the PHP equipment. It requires financial investment for infrastructure, equipment, technical training, equipment maintenance. There are centralized PHP facilities that can service growers, but just because they exist does not guarantee accessibility. There's limited facilities. Growers need to be able to get their goods there. They need to be in range of them. There's also the idea that generally the half-shell market wants very fresh oysters. There's the perception that oysters treated via PHP are not as fresh because they are dead. When generally you get an oyster on a half-shell, it's still basically alive. It was recently shucked. And additional misconceptions like perceived changes in texture, taste for some of the PHP treated products. And like I mentioned, consumers relate irradiation to radiation. So there's definitely a need to help preserve that small business, that independent characteristic of oyster farmers, while also providing them an accessible way to treat oysters against bacteria such as Vibrio. And also, keeping in mind that consumers prefer fresh oysters, but, we also want to give consumers the safest product as possible. So for my project, I propose the use of existing disinfectant technologies to help fill this gap, that applying existent readily available technologies to enhance traditional depuration to be effective both enteric bacteria and Vibrio. So I'm going to jump right into the 2 different sections of my thesis. I'm going to start with section 1, which I'll call paradigm technologies. So for this, I was utilizing recirculating aquaculture systems, which you'll see abbreviated as RAS, that were amended with 2 different disinfectant technologies. My main objective was to determine an effective method to measure the disinfection potential and output of my 2 technologies, which I'll go into more detail, but they'll be called the PBCO and PWT technologies alone and in combination. And ideally, I would be observing higher ozone measurements, which we'll go into more detail later about how I measured and so on. Higher ozone measurements in the PPCO treated RASes and greater voltage detected in the PWT treated RASes. So getting into the technology itself, the first one, the Pyridine Photocatalytic Oxidation Air System, which is the PPCO. This uses a reaction of UV light with a substrate coated in titanium dioxide to create free radicals, including ozone. They use a proprietary coating that produces a number of different free radicals, but ozone is a major component. It's been validated to be effective on a variety of different pathogenic microbes and viruses. Oxidants are already an established disinfectant agent in aquaculture and applied to a variety of organisms. Ozone is very common in aquaculture, and it can be applied to it can damage living organisms, so you have to apply it carefully, but generally that effect depends on the organisms in the system itself, and your dosage and exposure time. The second piece of technology is the Pyridine water technology, and that's that silver tube in the image to the right. And this is a magnetochemistry treatment system that produces nanobubbles. It uses rare earth magnets to reduce the surface tension of water and create nanobubbles from dissolved gases. It's thought that nanobubbles potentially stress microbes, they can produce oxidants when they collapse and disrupt the electrolyte activity and sodium-potassium pump of cell membranes. A combination of nanobubbles and ultrasound has been shown to be effective in reducing VP concentrations in vitro. And this is kind of the overall system design. So I had 5 RASes that were sitting in a common tank. So they were 100-liter fiberglass tanks. You can see them in the top left image. And then I had the same kind of basic 2-step filtration layout for each system, and then each one was amended according to the treatment or control. So the bottom left image, that's my UV control. I use it as a positive control since UV is a well-established disinfectant technology. So you can see the 2-step filtration with the UV unit going through a flow meter and then back into the tank. The middle image is my 2 PPCO units that were housed in the systems were originally designed for an HVAC system, so we housed them in an aluminum box that we created to mimic, a subsection of the HVAC system. So that was a sealed box, and air flowed through it and into the 2 treatment tanks. The image on the bottom right is the PWT treatment. You can see similar plumbing setup with the PWT unit installed in line. So for measuring the output, for the PPCO output, we were focused on measuring ozone. So we started with the indigo method and eventually transitioned to Hawk ozone AccuVac ampules. This was ultimately just because the indigo method was impractical to do in a realistic timeline when working with ozone. Since ozone is a difficult gas to work with, it has a very short residence time in water. So the ampules really helped me essentially do tank side measurements, which became really important when I go into the discussion a little bit later and really get into the difficulty of ozone as a gas. And for the PWT output, we were measuring voltage with the idea that the nanobubbles or the magnets were producing free energy in the water, and that would tell us if they were functioning or not. So I measured the voltage using a multimeter. And of course, my other parameters I took using a YSI multi-probe. So I was taking temperature, DO, salinity, pH, water and air flow were inline air and water meters. My goal was originally 3 replications for 3 different salinities, 0, 15, and 25 ppt. And I measured my parameters at 3 different time points, 0, 24 hours, and 48 hours. My results for this are largely in progress. Here's 2 summary tables. Generally, my ozone, I couldn't really get any ozone readings in the water, which I'll go into. Voltage, very variable, and ultimately, still working on processing that data. So initially, voltage was selected to determine free energy in water. There are a lot of other factors that can influence voltage, which may have contributed to the amount of variability that I've seen in the data. I also ended up having a smaller data size than I originally wanted due to sampling constraints. And really my main takeaway from that was that in the future, considering other methods to confirm the presence of nanobubbles would be really important, and also help determine, how link voltage to the presence of nanobubbles to really help ease sampling and measurement in the future. One potential process is dynamic light scattering. There's a number of different processes that can be used to detect nanobubbles. A lot of them require more complex physics and chemistry analysis. And I also, didn't get to test all of the salinities I wanted. So generally just increasing the salinities tested and replication size to maybe hopefully help eliminate some of that variability that I saw in the data. For the PPCO technology, as I mentioned, my ozone readings were largely negligible throughout the study. And we definitely encountered difficulty diffusing ozone into the recirculating systems. We made a number of different system modifications to try and help with that diffusion. We constructed a speech cone, which is pictured in the top left. We also switched from airstone diffusion to Venturi injectors to get the air into the tanks. Ultimately, our delivery system was likely not optimized for ozone. In a commercial aquaculture system, ozone is typically delivered using an ozone generator that's using a pressurized oxygen feed. We were not using pressurized air. We were using a blower to deliver our air to the tanks. Blowers, high volume, low pressure. And in general, pressurized air is more effective at saturating water with gases. You have more options with how you diffuse it, like fine pore diffusers. Our speech cone also failed because our system was just not initially designed to accommodate a pressured component, and speech cones typically operate under pressure. But generally, the concept of a speech cone is you have a cone, water enters from the top at a higher velocity. The cone increases in diameter, the water slows down. You're also injecting air into the cone at usually higher up in the cone. And as the water is coming in at a higher velocity, it's forcing those air bubbles down. And every time they try to rise up, they're just continuously forced down. So this essentially forces saturation. And speech cones are very effective at saturating water with gases. Another issue is that ozone is highly reactive. Its residence time in water can be as short as 2 minutes, depending on what's in your water. So it basically is going to, as soon as it hits water, react off with any organics in the water. So there's a threshold you need to overcome if you want to maintain a level of ozone in the water. So diffusion was likely our biggest issue. In the future, design and delivery should be the focus of continued effort to implement this technology. Be also useful to quantify the in-air output of the PPCO technology, not just validate its efficacy against viruses and bacteria, but also just what is it putting out into the air. And that was, information that we did not have. And ultimately, I ended up being unable to get my Hawk ampules to continue testing for ozone due to supply chain issues from, COVID. So we ended up kind of wrapping that portion of my thesis up a little earlier, just because we couldn't get materials. The next section of my thesis was using liquid smoke. So my objectives were to determine the minimum inhibitory concentration of liquid smoke to inhibit bacterial growth, determine the performance of different varieties of liquid smoke in inhibition, determine if pH of liquid smoke plays a significant role in inhibition potential. So taking a small step back, what is liquid smoke? So liquid smoke is a food additive derived from natural wood smoke. Historically, smoking has been used to preserve foods and impart flavor. It's produced via the condensation of wood smoke. And you can see in this image from Lingbeck et al., this is just a diagram of the process to make liquid smoke. Liquid smoke has some benefits over traditional smoking. You can further purify it, remove carcinogen. It has a high degree of flexibility, easy to apply and control concentration, and you can develop specific products around, the effects you're trying to achieve. There's the antimicrobial properties of liquid smoke have been validated in studies on food systems and in vitro against a large number of bacteria. It contains a variety of compounds thought to contribute to those properties. Primarily phenols, carbonyls, and organic acids are thought to be the most active compounds. The content of these in an individual liquid smoke product depends on the source of smoke and what was burned to produce it. And of course, the product itself, liquid smoke, is very concentrated. So there's different products with different concentrations, depending on, if you want it to smell really strong or taste really strong and so on. So my hypotheses were that I was using two varieties of liquid smoke, which I'll get into in the next slide, but that the hickory liquid smoke would have a lower minimum inhibitory concentration than the applewood liquid smoke, that the hickory smoke would overall perform better than the apple, and wanted to see, I suspected that pH played a significant role in inhibition potential because pure liquid smoke is fairly acidic. So I used two different varieties of liquid smoke, a hickory source smoke and an applewood source smoke. The reason I thought there'd be difference between the two is hickory is thought to have more phenols, which are thought to be primary components in those antimicrobial properties. Applewood smoke has less phenol content. So I thought that might contribute to maybe less inhibition activity from the applewood smoke. So I used two different methods to determine inhibition: a microplate reader assay, traditional plating methods. I used two varieties of liquid smoke, as I mentioned. I also performed pH adjustments using food grade sodium hydroxide to try and help reduce the acidity of of each smoke, to see with the role that pH actually played in inhibition. I mixed the liquid smoke with the LB broth media at two different percentages to create my treatment media. So I did a 2% and a 1.5% media. I used a Vibrio parahemolyticus strain, VP846. It was isolated from Washington in 2007, and it has both virulence genes. So for my microplate assay, I did 2 replications for each smoke percentage. I analyzed it in R using the growth curve package. So for my pH adjusted treatments, I adjusted the pH from 6 to 8. So you can see my treatments listed here. On the right is my layout of my microplate assay. I'm not going to go through each one individually, but I'll give you a second to look, since it is a rather large list, but we'll get more into that with my results. To help validate the microplate assay, I did some traditional plating methods. So we chose the 2% liquid smoke hickory based on preliminary microplate results. We expected to see no colony forming units at the end of 25 hours from cultures treated with the 2%. I did 2 replications of this with 6 time points over 25 hours and 3 dilutions at each treatment, for each treatment at each time point. And image to the right is just example of the different dilutions that were done at each time point. So jumping right into my results for the microplate assay. So this is for the 1.5% treatment growth curves after 35 hours. So you can see that there really wasn't a large amount of inhibition. The only treatment that saw complete inhibition of growth was the liquid smoke hickory that was pH treated. So this had a more neutral pH. The pH was around 6. And we didn't really see any inhibition otherwise. But jumping to the 2% treatments, we saw complete inhibition in both liquid smoke varieties and in both pH treatments. We saw that there was no growth of the Vibrio over 35 hours. In the 2% liquid smoke hickory plating, similar results. The image to the right is the control and the treatment plates. You can see the control, a typical growth pattern. And then the image to the left is kind of just a focus in on the liquid smoke, just because it was so much lower than the control. You You can see there was a little bit growth in the second replication, but by the end of 25 hours, there was no colony forming units seen in any of the plates. So overall, the 2% liquid smoke treatment was effective in inhibiting the growth of Vibrio in both microplate assays and traditional plating methods. The 1.5% showed less efficacy. Only the LSH pH adjusted was able to completely inhibit growth. More replication would be needed to really see if this was a one-time thing or like it's consistent, and really help explain why it would be the LSH pH. The pH generally was neutral, even between the pH adjusted and non-adjustment treatments, where it was, it was 6 before buffer, 8 after buffer. So fairly neutral either way. At a lower pH where, the smoke by itself before it's mixed with the media is around a 2 on the pH. So, if you're looking at it before that, it's very acidic. So if you're looking at it before you mix it with the media, it might play a way greater role in that. But after it's mixed with a buffer, it becomes fairly neutral. And we know that Vibrio can withstand a fairly wide range of pHs, so it doesn't necessarily explain why we only saw it in the 1.5% LSH pH treatment. And again, in the 2%, we didn't see an observable difference between the different varieties. And in the 1.5%, we did see difference between the LSH and LSA, with LSH performing better. I'm going to breeze through this really fast because I'm running out of time, but I already mentioned that system design is a critical component of implementing the PPCO and PW technologies. The next step for that portion of my thesis would be improving system implementation, starting from the ground up when you design a system to incorporate these technologies, and also improving our detection methods. And then for the liquid smoke, it did prove to be effective at inhibiting the growth of VP in vitro. Needs to be further explored to confirm its efficacy against VV and under different conditions. And my thoughts with that is you could potentially apply it to oysters in a depuration-like manner, oysters submerged in water containing a given percentage of the product, and then, but that would take a lot more evaluation. Do oysters even continue filtering activities when they're exposed to liquid smoke? But potential to produce uniquely flavored products that may also contain a lower pathogen load. Both are novel applications of existing technologies or products. Novel approaches are essential for tackling emergent issues in the aquaculture industry, and it's important to stay true to the independent nature and small business focus of the oyster aquaculture industry. Very quickly, just want to thank my advisor, Dr. Dennis McIntosh, Grant Blank from Delaware State University, who helped with constructing my RAS system, Ava Ellett Rose Adelizi, and Dr. John Jacobs from the NOAA Oxford Cooperative Laboratory, who helped me perform the second section of my thesis, and my committee members, Dr. Sigrid Smith, Dr. Kimberly Milligan, and Dr. John Jacobs, and Dr. Dennis McIntosh, and NOAA LMR CSC for funding this project.